Hello, today I'm going to be speaking about the use of derivatives. We use derivatives when we want to know the instantaneous speed at a given point. So let's say we have a car traveling at a constant speed of 1 meter per second, which is kind of equivalent to saying um, it's a linear function with this sort of formula. So we plug in 1, we get 1, then the speed increases to 2 at 2 seconds and 3 at 3 seconds. Now from this graph, since it's simple, I want it to be simple, but you can easily tell the instantaneous speed at 2 seconds, which is 2 meters per second. The speed at 3 seconds is 3 meters per second. So essentially what we do with the derivative is we find out the speed at a given point, any point we want, as long as our function is continuous. Now, what about acceleration? Well, in an ideal mathematical world, the acceleration of this function would be denoted as so, at the yellow line, so it would just be a constant function, but that is not how things work in real life. It takes a while to speed up to that given acceleration. So let's say in 1 second we got to 1 meter per second. So how would we find out the instantaneous speed, acceleration at given points? Again, we would use the derivative and we would derive our function and we would plug in our x value to get a specific output. Now I want to show you what velocity is and what acceleration is. So if we have a road which is, let's say, 10 meters in length, this is my road. We can denote it as S or X. It really depends on your taste. Um, our road is 10 meters long, and we can slice it up into smaller pieces. And we can slice it up into really small pieces, which is dx. And then our time on our timer, so let's say we have a 60-second clock, we can slice up our seconds into really small parts of a second, so let's say 1 millionth of a second, and we'll get dt. So what d always means is that we're taking a very small value. We're taking the derivative of a specific point, so we're approaching the point for both sides, and the difference from the point that is close to our point is very small. It's very tiny because you want it to be as precise as possible, as I said before. So essentially, acceleration is the change of distance over time. So a small change of distance over a small time, so that we get a very precise reading for a given point. So we're kind of, if you think about it, it's kind of like playing a movie with a car driving, and then essentially just cutting up the movie into really small parts, and we can tell how fast the car is going um, in those specific parts. Acceleration is telling you the change of velocity over time, so how fast we are changing our speed. Now let's go on to a more let's have a look at the use of derivatives in mathematics. We use derivatives to find saddle points. That's when our function changes. So a saddle point in, let's say, a crazy function like this is essentially the point where our function starts changing. So let's say around here. It's not really a good example. I'll give you another example. So let's say we've got a crazy function like this. A saddle point would be around here. Another saddle point would be around here. It's basically where we change from decreasing to increasing, where the function is changing from decreasing to increasing. So if this point at this point we're changing from decreasing to increasing, what do you think the value is going to be for the second derivative? So we derive our function twice. The value is going to be 0. So when we have a saddle point, our second derivative is equal to 0. It means that the slope of our function is not changing. It is neither increasing nor decreasing. With extrema, we have to be careful, obviously, because let's say we have a function where in the middle of our function we get a saddle point. So our derivative is equal to 0. Then what will happen? What will happen is that we'll think that we've hit our local minimum, or in this case local maximum, but as you can see the function still carries on, so we don't really have a maximum because it's still growing and it's growing into infinity. So we must not confuse ourselves and think that we've hit our extrema. Now let's find, as an example, so that I make sense of this for you guys, let's find the extrema of this function. So I will derive. In the previous video I've shown how to derive this, and I've explained what a derivative is. So if you want to know what a derivative is, please check out my other videos. So we derive this. Derivative is 2x plus some really small number, but we don't really count that in. And what we do is we sort of look at our domain, the domain of our function, where our function is defined from minus infinity to plus infinity, so all real numbers. And we just plug in some x values. That makes sense. So our function changes around the point 0. That's where we are neither increasing nor decreasing. The derivative of that point is 0. If you plug in 0, 2 times 0 is 0. So our slope is 0. We're not changing. It's just a straight, constant line. We know that our values are negative on the left hand side and positive on the right hand side. So essentially what this means is our function is getting larger on the right hand side from 0, and it's getting smaller from the left hand side to 0. So from minus infinity to 0, and then from 0 to plus infinity is getting larger. So how do we know if we have a maximum? Well, let's just plug in the values at our interesting point. The thing you want to focus on is points where you have 0, the slope 0, where our function is neither increasing nor decreasing. Because you'll have functions like this, where let's say this is our largest point, and the derivative at this point, let's call it x0, is 0. This is the point x0. Exactly at this point is where we want to be focusing. We've got loads of other saddle points, like this point, which is our lowest point. And what we want to do is plug in values slightly after it and slightly before it. So in this case, if I want to find out if this has a local maximum, I've derived my function. What happens when I plug in values of x which are larger than 0? I get numbers like 2, 4, 2 times 3 is 6, 8, and so on. So it's getting larger. What happens when x is smaller than 0? It's getting smaller. So 2 times minus 1 is minus 2, minus 4, minus 6, minus 8, and so on. So as we can notice, our slope is getting smaller and smaller the more we travel in this direction, and it's getting larger and larger the more we travel in this direction. again, we were looking at points around our saddle point, which is 0. We were focusing on this small area, from this interesting area from, let's say, 8 to 0, and then from 0 to -8. Sorry, -4 on the x-axis. I was speaking about the slope. So what can we find out from this? Is that really we don't have a maximum, because if we plug in values into our function, like let's say 1, we get 1. If we plug in 2, then we get 4. So our function is still getting larger, so this cannot be a local maximum. And if we plug in negative values, our function is still getting larger. So our y-axis is getting larger and larger numbers as well, if I just denote that. So let's say I plug in -1, I get 1. If I plug in 2, -2, I still get 4. So on both sides our function is getting larger on the y-axis. It is, however, not getting smaller than 0. So if it's not getting smaller than 0, we can say with confidence that our local minimum is 0. That's all for today, guys. Thank you for watching. Please like, share, and subscribe. See you next time.